Good day, folks. Welcome to my YouTube channel. Those who are new here, welcome. Don't forget to subscribe, like all my videos that you're watching. Watch them till the end, and don't skip the ads. The returning subscribers, welcome back. Continue doing the right thing. Don't forget to skip to watch the ad. Don't skip them, and like and comment. Right. Okay, this is question 8 in the Gauteng province, which is the 2024 trial question paper. Let's cut the chase. It says a galvanic cell constructed shown in the diagram below. So we have a galvanic cell here. We have a nickel electrode and the cadmium electrode. Right. If you go to the table and check which one is oxidizing and which one is reducing. So we see the cadmium there and we see the nickel there. This is table 4b, guys. We know in the table 4b the one that is on top is oxidation. So this is oxidation, so the cadmium is oxidizing and the nickel is reduced there. Alright, so this is an anode and this is negative and this is positive and it's a cathode, right? And a reduction takes place in the cathode and oxidation takes place in the anode, right? It says which one of the which electrode is cathode. So the cathode is what is nickel, right? It says write down the oxidation half reaction of this cell. So it's cadmium that says that is oxidizing. It's going to be Cd2 plus the 2 electrons. Even on a table it's like that, and we're writing it this way, right? Now in 8.1.3 it says how will the reading on the voltmeter be affected if the concentration of nickel ion is increased after the cell has reached equilibrium, right? Choose increase or decrease or remain the same. Give reason for your answer. So what is best to do this is to write the ionic cell or the net. So it's gonna be nickel 2 plus Cd. It's going to be Cd2 plus nickel, right? So now it says this, the nickel ions is increased. So when the nickel ion is increased, the system, according to Le Chatelier's principle, is going to decrease that. So that means the reactants decrease and the product is going to be what? Increase, which is the cadmium ion is going to increase. So here forward is going to be favored. The concentration of product is going to increase. So the answer here is what? Is increase. And then your reason, you say forward reaction is favored by the increase of nickel ion. Forward reaction is favored, right? 8.2 it says consider the following standard electrochemical cell. We have the net cell here. This is the cell notation. So we know in the cell notation this is an anode, so that means the copper is oxidizing, and the silver is the cathode. That means the silver is reduced. It says initially each cell contains the 200 cubic centimeter, which is its 0.2 dm3. So each electrolyte, it's a galvanic this, each electrolyte, its concentration, its volume, since they say its concentration is going to be 1 mole per dm3, 1 mole per dm3, and the volume of each, it's going to be 0.2 dm3. The volume of each is 0.2 dm3. Where do we get the 0.2 dm3? Is the 200 we divided by 1000. Now it says the cell is connected to the circuit and allowed to produce the current until the concentration of an electrolyte in the cathode half cell is reduced to that. So this is the concentration of the what? Of the silver ion. right? This is the concentration of the silver ion reacted. And then it says the cell is then disconnected. So when the cell is disconnected, they said write down the equation, the balance equation for the net ionic. So we know the oxidation is what is Cu, and what is reduced is silver. And how many silver? It's 2 silver ion, and then it's going to be Cu2 plus. When the copper is oxidized, it's going to oxidize to Cu2 plus, and the copper is going to reduce into silver ion, 2 of them, right? Now in 8.2 it says calculate the concentration of an electrolyte in the half cell when the cell is disconnected. So in the anode half cell. So we're going to start with the cathode answering this question. In the cathode, what is happening in the cathode here? The cathode is silver ion gains an electron and become a silver in a solid state. Now what we do here, we have we're going to calculate the concentration. From the concentration, this is the concentration of silver. From this concentration of silver, we're going to calculate the number of moles of silver that reacted, which is Cv. That means, in other words, we're changing from concentration to number of moles. So the concentration is 0.5, and we times by the volume, which is 0.2, which is going to be 0.1 mole. So this is the concentration of silver reacted, right? This is the silver that reacted, which is this silver that is reacted. So getting this silver that is reacted, we can simply get the copper ion that is what is oxidized, doing the mole ratio there. So what are we going to do? We're going to we can say, since the mole ratio you can see here is 1:2 in order to get the copper that is reacted there, so we can say the number of moles of copper, the copper that is what reacted, is going to be the half of the number of moles of silver ion reacted. Where do we get that? Because the ratio is 1:2, so it's going to be half times 0.1, which is going to be 0.05 mole, which is the number of moles of copper reacted using the silver ion reacted, right? From that, we can go to an anode now. Going to an anode, we know the reaction of an anode. It's a copper oxidizes to Cu2 plus 2 electrons. Now that we have the copper that is reacted, it can give us the copper ion that is formed. You can see the ratio here is 1:1. So we can simply say the number of moles of copper ion, what is the copper? The copper ion that is formed is equal to the number of moles of copper that is what? That is reacted. Since the ratio is 1:1, they're going to be equivalent. The copper that reacted is going to be 0.05 mole. So the copper ion that is formed when the copper oxidizes, it forms this one. So the copper that reacted is the same copper that is formed, because the mole ratio is 1:1. Okay, so from that we can calculate the initial number of moles, the initial number of moles of what? Of copper 2 plus, the initial number of moles using the concentration. We know the concentration, as I've mentioned, the concentration of silver ion at standard electrochemical cell, it's 1 mole per dm3, and the concentration of copper ion, it's 1 mole per dm3 initially. So I'm going to calculate the number of moles the number of moles of copper ion, which is I'm gonna use this concentration. It's gonna be 1 times the volume. What was the volume? It was 0.2, right? 0.2, which is going to be 0.2 what mole. This is the number of moles that was initially there. So in order to get it's 0.2. So now in order to get the final, which is the amount that is left at equilibrium, we can say the number of moles of copper ion, 2 plus. The question, it says calculate the concentration of in an electrolyte half cell when the cell is disconnected. So we want it at equilibrium. In other words, this is the what? This is the final. So we'll say the number of moles of copper 2 plus, which is the initial one, and plus the number of moles of copper 2 plus, which is the one that is what is formed, right? The one that is formed, that will be the initial, and the one that is formed. So the initial is 0.2 and plus the one that is formed, which is going to be 0.05, which will give us the 0.025 mole, and then we change that into a concentration. So we'll say the concentration of Cu2 plus, which is the final, is N over V, which is it's 0.25 divided by the volume. The volume that will be given, it's going to give us 125 mole per dm3, right? So when the cell is disconnected, the concentration of an anode electrolyte is going to be that, right? Let's look at it this way, guys, using the table. So the ratio here, what we're going to focus, if you get the net cell there, so this is a solid state, we're not going to focus on that, and this is the solid state, we're not going to focus on that. I'm going to focus on the aqua, right? On the 2 aqua. What is the ratio? It's 2:1. 2:1, right? What is the initial number of moles? The initial number of moles of both of them, as I've mentioned, the concentration of silver ion is equal to the concentration of copper ion, which is its 1 mole per dm3 in a volume. What is a volume? The volume there that we given, it was 0.2 dm3. So if we change that into number of moles, the number of moles of Cu2 plus is equal to the number of Ag2 plus, which is gonna be, it's gonna be when we say Cv, which is at 0.2 times 1, which is the concentration, is gonna be 0.2. So the initial number of moles there is 0.2, right? And the change is the number of moles that reacted. The number of moles that reacted, we were given for silver, the number of moles of silver ion there, which is Cv, the concentration, it was 0.5 times the volume, which is 0.2, which was 0.1. So for silver it's 0.1, and then which is 0.1, and we got the number of moles that reacted from the 0.1, the number of moles that reacted for. So if you are looking even in the mole ratio there, it's Ag plus is to Cu2 plus, and is 2:1, and then we looking for Cu, we put X, and then we have 0.1 there. We're doing a mole ratio for this, so we cross multiply with 2x times that. It's going to be X is equal to 0.05, so it's 0.05 there. So the concentration, this is what we want. This is what we want. The concentration when the cell is disconnected, which is, this is the number of moles. This is what we want, in fact. This is the number of moles of equilibrium. We wanted the concentration at equilibrium when the cell is disconnected in an anode, and the anode is that one. So this is the reactant, so we're going to say 0.2 minus the 0.1, it's going to be 0.1, and then we'll say 0.1 divided by 0.2, which is the volume, is going to be 0.5. So since this is the product, you can see this is the product. In the product, what do? We add, it's 0.2 times plus 0.25, so it's going to be 0.25, we divide by 0.2, no, it's going to be 0.25, and then here it's going to be 0.25 divided by 0.2, it's going to be 1,25. That means we got the answer. This is the answer there. I hope, guys, that makes sense. By that,